What if I told you the secret to teaching an AI to write like perfect, flawless software code
Right.
is to actually train it on code that hasn't even been tested?
I mean, it sounds completely backwards, but the data we are looking at today proves it actually works.
Well,
We're completely rethinking how neural networks learn complex skills.
yeah, and if you're listening and you have ever tried to use an AI coding assistant on a sprawling proprietary company code base, you already know the profound frustration of it all.
Oh,
You
absolutely.
ask the AI to fix a bug, and it confidently writes this beautiful piece of code that is just, well, utterly
Yeah,
useless
it completely misses the mark.
because it fails. The
Yeah.
AI has absolutely no idea about the undocumented, sort of quirky logic baked into your company's private repository over the last decade.
Right. The stuff that's not on GitHub.
Exactly. And you can't exactly just upload your company's core intellectual property to a closed cloud model to give the AI context. I mean, the security team would have a collective heart attack.
Oh, for sure. You'd be fired by lunch.
Right. So you feel stuck?
And that's because the smartest frontier models in the world are essentially flying blind the moment they step outside the public data they were trained on.
But today's deep dive into the source material is going to show you how this problem just got solved.
It really did.
We are looking at this groundbreaking paper from researchers at the Allen Institute for AI-A2, along with the University of Washington and Carnegie Mellon University.
Some heavy hitters.
Yeah. And our mission today is to explore a revolutionary new method they've developed called SERA, which stands for Soft Verified Efficient Repository Agents.
Right. And SERA essentially makes training AI coding agents on private proprietary code bases radically cheaper, faster, and way more effective.
It's a huge shift.
It takes something that was previously a pipe dream for anyone without massive Google-level funding and puts it right on your local machine.
Okay, let's unpack this. Because
Yep.
historically, if you wanted to teach an AI to autonomously solve complex software engineering tasks,
Right, like real tasks.
yeah, not just auto-complete a line, but actually navigate a repository, read files, and resolve an issue, you basically had two brutally expensive options.
Yeah, the primary methods were reinforcement learning, or RL, and synthetic data generation using strict unit tests.
And both of those are just so hard to pull off.
Massive barriers to entry. Let's look at RL first. You are essentially letting a model trial and error its way to success.
Which sounds incredibly dangerous with code.
Exactly. To do that safely, you have to build incredibly complex infrastructure. You need sandboxed execution environments because if the AI tries a random command to fix a bug, it might accidentally execute a script that wipes your entire server.
Oh, wow. Yeah, that would be bad.
Very bad. And you also need distributed training infrastructure just to coordinate all these rollouts and the mathematical gradient updates to the model.
So it's basically like building a massive, highly regulated, simulated city just to teach someone how to drive.
That's a great way to put it.
You have to program artificial traffic jams, build mandatory crash test facilities, hire a fleet of safety monitors. I mean, it is just way too expensive for a regular local driving school.
The infrastructure overhead is just staggering.
Yeah.
I mean, the source papers we look at for RL coding agents, things like SWE-RL or SkyRL agent, they often have author lists of 12 or more people,
12 people just for one paper.
simply because it takes an entire engineering department just to manage the complexity of that training environment.
That's insane.
And the alternative, traditional synthetic data generation, isn't much easier.
Okay, so that would be methods like the SWE Smith pipeline, right?
Right. With those pipelines, you have to programmatically inject bugs into a code base that currently has passing unit tests.
Okay.
Then you have the AI try to fix the bug,
Hmm.
and you run the test suite again to see if it passes.
So you're constantly running these tests.
Exactly. You are completely bottlenecked by the need for rigorous, flawless test environments. The researchers note that previous RL methods cost around $18,360 in compute just to train.
Wow.
Yeah, and even S.W. Smith's synthetic data pipeline cost about 52 cents per trajectory when using a top-tier model like Claude 3.7.
And 52 cents doesn't sound like a lot until you realize you need, what, tens of thousands of examples?
Exactly. When you need tens of thousands of examples to teach a model, that barrier concentrates AI development entirely in the hands of massive, well-resourced industry labs.
Which leaves the rest of us entirely dependent on their generalized cloud models.
Pretty much, yeah.
But because that simulated city of strict unit tests was just way too expensive, the SERA researchers had to completely rethink what makes a good training example for an AI.
Right. They bypassed the bottleneck entirely by introducing a concept called soft verified generation, or SVG.
SVG, okay.
And it completely removes the need for executing code or running unit tests during data generation.
Wait, I have to stop you there. Because if you aren't testing the code, how do you know the AI did anything useful? Like, how are you verifying it?
It's such a good question. The mechanism relies on a two-rollout process using a highly capable open-weight teacher model. In this case, they used GLM 4.5 Air.
Okay, so a teacher model.
Right. For the first rollout, they point this teacher model at a random function in the code base and give it a deliberately vague bug instruction.
Vague like what?
They might tell it something open-ended like fix code clarity, rather than pointing to a specific broken loop.
Oh, interesting. So the model goes in, makes a change, produces a trajectory, which is, a step-by-step reasoning process, and outputs a final code patch.
Exactly.
And then they take that trajectory and use it to write a synthetic pull request, essentially like a fake GitHub issue describing the structural change it just made.
Spot on. Then comes rollout 2. They wipe the slate clean.
Okay.
They give the teacher model only that synthetic pull request description, and they ask it to recreate the patch it made in the first rollout.
Okay. Here is where the absolute magic of soft verification comes in. Let me see if I have this right.
Go for it.
Instead of taking that new patch, spinning up a sandbox, compiling the code, and running a battery of unit tests to verify it works, they just look at the two patches and check for overlap.
That's it. They use a simple mathematical recall calculation. They're looking at the target lines of code and asking, did the AI's second attempt hit at least half the same lines as its first attempt?
Just half.
Yeah. If it hits a 50% match, they consider the trajectory verified and add it to the training data.
Okay, I have to push back here on behalf of anyone listening who writes production code for a living.
I knew this was coming.
Wait, so we are training an AI on code that hasn't even been properly compiled or tested?
Yeah.
We don't even know if it functions. Isn't that just teaching the AI to write sloppy, broken code?
It really seems like it should, right? But the data reveals something incredibly counterintuitive about how neural networks actually internalize complex tasks.
Okay, what did they find?
The researchers ran what is called an ablation study. That is essentially a brutal game of Jenga, where researchers start pulling components out of their training process to see when the whole system collapses.
Okay, I like the Jenga analogy.
They compared hard verification, where the patches match 100%, against soft verification at 50%, and even 0% match. Completely unverified trajectories.
Wait, so they threw literal garbage at the model just to see what would happen?
Literally unverified junk.
And what were the results?
The performance was identical.
Wait, really? Identical?
Identical.
Yeah.
The models trained on soft verified and unverified trajectories performed just as well as those trained on strictly verified data.
That's crazy.
They tested this against SWE-bench, which is basically the ultimate gold standard SAT-style exam for AI software engineers.
That is wild. How is it possible that a model learns to code perfectly by studying broken code?
The value of the training data isn't in memorizing the final, perfectly correct syntax. The model is learning the workflow. It is learning how to navigate a complex directory structure, how to use its view and edit tools, and how to translate a high-level intent into a localized edit.
Oh, I see.
Think of it like teaching someone to use a library. If you teach them how the Dewey Decimal System works, how to use the index, and how to scan a shelf, it doesn't matter if the first book they pull out is the wrong one. They have mastered the skill of finding information.
That makes total sense.
Right. Once the AI masters the workflow, its inherent language capabilities allow it to solve the actual bugs on its own.
Wow. So because they threw out the unit tests and the sandboxes, data generation suddenly becomes incredibly cheap.
Exactly.
You just need an API or a local GPU running the teacher model. You don't need a massive simulated city anymore.
And that cost reduction allows you to change your entire strategy. When data is cheap, you don't need to build a generalized model anymore.
Right.
You can point this SVG pipeline at a single specific proprietary code base and flood a smaller model with data specific to just that one environment.
And the source material highlights how those vague instructions from the first rollout play a crucial role when you specialize on one repository.
Oh, totally.
Because if you tell the AI fix state management or improve documentation, it performs highly realistic structural tasks.
Yeah, it's not just fixing typos.
Right. It does real-world refactoring tailored to your company's specific naming conventions and architecture.
And the performance gains from this repository specialization are just staggering. The researchers took a 32 billion parameter open weight model, Q3.
Okay, meaning its neural weights are downloadable, right?
Exactly. It could be run locally, completely isolated from the internet. They specialized it on specific repositories from the benchmark, like Django and SIMPy.
And what happened?
By generating just 8,000 synthetic trajectories from a specific repo, this smaller student model didn't just improve. It matched or exceeded the performance of its massive teacher model on that specific code.
So what does this all mean for a small startup or, a solo developer? Can a tiny engineering team with a local server really beat a multi-billion-dollar frontier model on their own turf?
If we connect this to the bigger picture, there is a fundamental architectural advantage at play here that allows a tiny team to win.
Okay, what is it?
A specialized student model has the repository's specific patterns, conventions, and domain knowledge baked directly into its neural weights.
Right.
A generic frontier model, no matter how massive, can only read the code base temporarily by holding fragments of it in its context window.
I get it.
It's the difference between a local who's lived in a city for 10 years versus a genius with a photographic memory who just looked at a tourist map of the city for 5 minutes.
That is a brilliant way to put it. The local instinctually knows the shortcuts, the one-way streets, which bridges are closed for construction.
Exactly.
And the cost to become a local is just mind-blowing here. The source shows SERA achieved this single repo specialization for about $1,300.
Which is nothing in the AI world.
Right. And if you want to train a general model to match something like Devstral Small 2 on the global SWE-bench, it costs about $9,000.
Yeah.
That is 26 to 57 times cheaper than older RL and synthetic methods.
The entire field becomes democratized at that price point. However, I should point out, generating cheap data is only half the battle.
Okay, what's the other half?
Well, if you throw a mountain of cheap data at a neural network improperly, you usually get garbage out. Knowing exactly how to process that data before feeding it to the model is where the real secret sauce lies.
Right.
The researchers discovered massive hidden traps in how we handle context truncation and reasoning.
Let's get into truncation because this is fascinating. Anyone who has used these agents knows they generate a massive amount of text.
Oh, pages and pages.
They look at a file, read the output, search another file. These interactions easily exceed 32,000 tokens, and a token is essentially a piece of a word. 80,000 tokens is the length of an entire novel. But a lot of smaller open-weight models have a strict 32K context limit. They physically cannot read the whole interaction.
Exactly. So you have to cut the training data down to fit.
And how were people doing it before?
The standard practice across the industry has just been to slice long trajectories to fit the window. If you have an 80,000 token interaction, researchers would often just grab a random 32K slice from the middle and feed it to the model.
Just a random chunk.
Yeah. But the SERA researchers hypothesized that not all slices are created equal.
And they found that if you randomly slice it, performance absolutely tanks.
Completely tanks.
They discovered you need a truncation ratio of around 0.95, meaning mathematically you absolutely must preserve the early problem-solving steps of the trajectory.
That's the key.
If you chop off the beginning where the AI is first figuring out the problem, the data is essentially poisoned.
Because the final steps of a coding trajectory are usually just the redundant mechanics of submitting the patch. The real intellectual heavy lifting, the exploration, the dead ends, the realization that a specific file is a dead end, that happens early on.
Makes sense.
If the network doesn't see the mistakes and the pivots, it never learns how to actually problem solve.
Okay, here's where it gets really interesting. It's like learning from a master chef.
I love this.
If you only watch them plate the final dish, putting the garnish on top, you learn nothing about cooking.
Exactly.
You absolutely need to hear their inner monologue as they taste the soup, realize it needs more salt, add a dash of acid, and adjust the recipe from the very beginning. If you don't see the struggle, you can't replicate the masterpiece.
Your chef analogy leads perfectly into their second major discovery about data processing, the absolute necessity of reasoning traces.
Okay, reasoning traces. What are those?
The researchers ran another ablation study where they took the training data and stripped out all the AI's internal reasoning.
The inner monologue.
Right. They removed that inner monologue where the AI says, okay, I see the errors in line 40. I need to check the import statement next. They deleted all of that.
And just kept the code.
Yeah, they only trained the model on the final code edits, the actual tool calls.
So using our analogy, they forced the AI to only watch the plating of the dish.
Exactly.
Yeah.
And the results were catastrophic.
How bad?
The resolve rate on SWE-bench plummeted from 41% down to 23%.
Wow, it almost cut it in half.
It essentially halves the capability of the model.
Mm.
A neural network doesn't just need to see what action was taken. It desperately needs to see why it was taken to build a predictive pattern.
That makes a lot of sense.
And because understanding this mechanism is so vital, the SERA team didn't just publish a paper. They released their entire data set of 200,000 trajectories to the public.
That's awesome.
Yeah, they want the broader research community to study these exact nuances of reasoning and context truncation.
Which is an incredible win for open science. But I want to pause on those performance numbers for a second.
Yeah.
Hearing that a 32 billion parameter model beat a massive frontier model by hitting 41% sounds almost too good to be true.
It does sound high.
And as we are reading through this paper, they drop a bit of a bombshell about how AI research is actually conducted today. How do we know these researchers didn't just get lucky on their test runs?
This raises an important question about how we actually evaluate AI.
Yeah.
Because the SERA paper exposes a major, often unspoken flaw in current AI coding research.
Yeah.
The single seed illusion.
The single seed illusion.
Yeah. When researchers evaluate a model on a benchmark like SWE-bench, there is a massive amount of run-to-run variance.
Okay.
An AI agent might successfully solve a complex bug on Tuesday, but if you run the exact same agent on the exact same bug on Wednesday, it might randomly take a slightly different path, get stuck in an endless loop, and fail.
Wait, are you saying that a lot of AI research out there might literally just be researchers taking a lucky dice roll, getting a slightly higher score by chance, and calling it a massive technological breakthrough?
The math suggests exactly that.
Wow.
A model might look 3% better purely by statistical chance, and yet many published papers in the field claim state-of-the-art breakthroughs based on a single test run.
That is wild.
If the natural variance of the test is 1 to 3% and your claimed improvement is 2%, you haven't proven anything. You've just captured noise.
So how did the SERA team prove they weren't just getting lucky?
They adopted an incredibly rigorous mathematical methodology. They proved that to ensure an improvement is mathematically real, meaning it has a high signal-to-noise ratio, you need to run at least 3 random seeds or separate evaluations for every single condition.
Okay.
They ended up running 234 individual evaluation runs across 78 conditions to back up their data.
But they didn't just run it more times. The paper mentions they use scaling laws and power curves to prove their point.
Right.
Can you break down what that actually means in plain English?
Think of it like the laws of physics. If you throw a baseball, gravity and momentum dictate a very specific parabolic curve.
Okay, I follow.
If you track the ball's position and every data point lands exactly on that mathematical curve, you know you are observing a fundamental law of nature, not just a random gust of wind.
Right.
In AI, a scaling law predicts exactly how much smarter a model should get as you feed it more data or compute. The SERA team plotted their performance improvements against these predictive power curves.
Oh, I see.
Because their real-world results hugged that mathematical curve perfectly, they proved their method was a genuine predictable signal.
Not just a lucky dice roll.
Exactly. Their efficiency and cost-saving claims are absolutely ironclad.
So, synthesizing all of this, the SERA paper fundamentally changes the math on AI coding agents.
It really does.
It proves that you do not need a massive compute cluster, a 12-person orchestration team, or a fragile, complex unit test infrastructure to build a world-class coding assistant.
Not anymore. Through the brilliance of soft verification and leveraging vague instructions, the primary bottleneck has been removed.
Which is huge.
Any team, regardless of their budget, can now affordably train an AI that truly masters their private code base.
And that is deeply empowering for you, the listener. It means the future of AI isn't just massive, generalized cloud models that you have to blindly trust with your proprietary company data.
Right.
The future is small, highly specialized, open-weight models living securely right there on your local machine, understanding your team's specific work better than anyone else in the world.
It is a massive step forward for data privacy, security, and raw developer productivity.
Absolutely. But before we wrap up today, I want to leave you with a final, slightly provocative thought to mull over.
Ooh, let's hear it.
We learned today that soft verification, which is essentially just judging an AI on the process and the shape of its work, rather than testing its final correctness,
Right.
is actually enough to teach it to write flawless code. It learns the workflow first, and the accuracy actually
The
follows.
Dewey Decimal System.
Exactly. So, what other highly technical human professions could AI master simply by mimicking the workflow without ever taking a formal test?
Oh, wow.
If it doesn't need a compiler to learn software engineering, could an AI learn architectural design simply by studying the drafting process?
That's a great question.
Could it learn complex legal strategy just by ingesting the inner monologue of a lawyer prepping for a case? If capturing the inner monologue in the workflow is all it takes to build a master chef,
Hmm.
what else is about to be served?